Welcome, fellow traveler of the night. If you found your way here, you're seeking something special, a journey through the cosmos that soothes the mind while igniting quiet wonder. Tonight, we'll explore one of the universe's most captivating mysteries, black holes. Those invisible giants that bend reality itself, where time slows to a whisper and light cannot escape. But don't worry, this won't be a lecture. Think of this as a conversation between friends, shared in the gentle darkness before sleep. We'll wander through facts that surprise and delight, through mysteries that scientists still debate, through discoveries that remind us how beautifully strange our universe truly is. No equations, no anxiety, just pure wonder. Before we begin, if you enjoy these cosmic lullabies, a gentle like helps others find their way to peaceful sleep. And if you'd like to join our community of dreamers, subscribe for more journeys through space and time. But for now, dim your lights, settle into comfort, and let your breathing slow. Let's begin our descent into the beautiful mystery of black holes. The nearest black hole to Earth sits just 1,600 light-years away. That might sound impossibly distant, but in cosmic terms, it's practically in our neighborhood, closer than most stars you see twinkling in the night sky. This sleeping giant, called Gaia BH1, weighs about 10 times more than our Sun. Yet it makes no sound, emits no light, reveals itself only through the gentle dance of a companion star orbiting its invisible embrace. Imagine something that massive, that powerful, hiding in plain sight among the constellations. But black holes weren't always accepted science. Just a century ago, even Albert Einstein doubted they could exist. In 1915, when Carl Schwarzschild first calculated that Einstein's equations predicted these impossible objects, Einstein dismissed the idea as mathematical curiosity, nothing nature would actually create. The universe, it seemed, had stranger ideas than even Einstein imagined. A beautiful reminder that reality often exceeds our wildest theories. And here's something that will make you pause. The smallest black holes are only about 15 miles across. These stellar mass black holes, formed from collapsed stars, pack more mass than our Sun into a sphere the size of a small city. You could drive across one in 20 minutes. Yet you'd be crossing an object so dense that a teaspoon of its matter would weigh more than Mount Everest. The impossible made real, compressed into a space you could almost hold in your mind. But what exactly is a black hole? At its heart lies the singularity, a point of infinite density, where all the collapsed matter concentrates. Around this sits the event horizon, the boundary of no return. Cross that invisible line, and not even light can escape. The event horizon isn't a physical surface you could touch. It's more like a one-way door in space-time itself, a threshold beyond which the laws of physics, as we know them, begin to whisper secrets we're still learning to hear. A door that only opens inward, into mystery. The event horizon of the smallest black holes measures just 30 miles in diameter. That's roughly the distance from downtown Manhattan to the far edge of Brooklyn Drive you might make in an hour on a Sunday morning. Yet, within that modest circle, gravity becomes so extreme that time itself nearly stops. If you could somehow hover just outside this boundary and watch the universe beyond, you'd see stars being born and dying in fast forward, civilizations rising and falling in heartbeats, while for you only seconds passed. Time becomes elastic at the edge of forever. Supermassive black holes tell a different story entirely. The monster at the center of our Milky Way galaxy, called Sagittarius A*, pronounced Astar, weighs 4 million times more than our Sun. Its event horizon stretches about 15 million miles across roughly the distance from the Sun to Venus. You could fit Earth's entire orbit inside it several times over. Yet, despite its enormous mass, this giant sits quietly at our galaxy's heart, occasionally snacking on wandering gas clouds, mostly just existing as the gravitational anchor around which 200 billion stars slowly dance. A gentle giant, relatively speaking, at the heart of home. But Sagittarius A* is modest compared to the true titans. The black hole at the center of galaxy M87, about 55 million light-years away, weighs 6.5 billion solar masses. Its event horizon is so large that light would take about 3 days to cross it. Imagine a sphere so vast that even moving at the universe's speed limit, you'd need 72 hours to traverse it. This is the black hole we famously photographed in 2019, that glowing orange ring that made headlines worldwide, the first direct image of a black hole's shadow against the bright matter swirling around it. The invisible made visible, finally brought into light. That photograph required 8 telescopes spread across the entire Earth, all working together to create a virtual telescope the size of our planet. Even then, the image took 2 years of data processing to produce. What we saw was not the black hole itself, which emits no light, but the glowing accretion disk of superheated matter spiraling around it, gas so hot it glows at millions of degrees, bright enough to outshine entire galaxies. The darkness defined by the light it devours. Black holes grow by feeding. When matter falls toward a black hole, it doesn't simply disappear, forms an accretion disk, spiraling inward like water circling a drain. But unlike water, this matter accelerates to nearly light speed, friction heating it to temperatures exceeding 10 million degrees Celsius. At these extremes, atoms are torn apart, electrons stripped away, matter transformed into plasma that glows brighter than anything else in the universe. The hottest, brightest things we know, all dancing around absolute darkness. Some black holes are surprisingly quiet eaters. Sagittarius A*, despite its enormous mass, consumes matter at a gentle trickle only, about the mass of a small asteroid every few thousand years. It's like a cosmic whale that barely opens its mouth, letting the occasional cosmic krill drift in. This docile feeding is why we exist. If our galaxy's central black hole were a messy eater, the radiation from its feeding frenzy would likely have sterilized much of the galaxy, including our corner where life arose. Silence at the center, allowing whispers at the edges. But other black holes feast violently. When a black hole actively devours matter, it can create a quasar object so luminous it can outshine its entire host galaxy. The brightest quasars emit more light than 1 trillion suns combined. These cosmic lighthouses can be seen from across the universe. Beacons from the early cosmos, when black holes fed more readily on the dense matter of a younger universe. Ironically, the darkest objects create the brightest beacons. Jets of matter shoot from some feeding black holes at nearly the speed of light. These relativistic jets can extend for hundreds of thousands of light-years, piercing through the galaxy and far beyond. The mechanism works like this. As matter spirals toward the black hole, powerful magnetic fields funnel some of it about 10% or so away from the event horizon, launching it outward in 2 opposite directions along the black hole's spin axis. These jets carry immense energy, sometimes containing more power than the rest of the galaxy combined. The eater becomes the fountain, paradoxically spewing what it consumes. Here's something that might make you smile. Black holes aren't cosmic vacuum cleaners. They don't roam space, sucking everything up. If our sun suddenly became a black hole, which it can't, its too small Earth would continue orbiting exactly as before. The gravitational pull at Earth's distance wouldn't change at all. We'd freeze in the darkness, certainly, but we wouldn't be pulled in. Black holes only consume what ventures very close to them, within a few times their event horizon radius. Gravity remembers mass, not the form it takes. The smallest black holes we know of weigh about 3 times the sun's mass. This isn't arbitrary, it's a fundamental limit called the Tolman-Oppenheimer-Volkoff limit. When a massive star collapses, if the remaining core weighs less than about 3 solar masses, other forces can resist the collapse. Neutron stars form instead, held up by quantum pressure. But beyond that threshold, nothing in physics can prevent the collapse. The core continues shrinking past the point where atoms exist, past where neutrons can survive, past all resistance, until it becomes a singularity wrapped in an event horizon. There's a mass where nothing can say no to gravity anymore. Stellar black holes form in the violent death throes of massive stars. When a star, at least 20 times more massive than our sun, exhausts its nuclear fuel, there's no longer enough outward pressure to resist its own gravity. The core collapses in less than a second. One moment it's the size of Earth, the next it's compressed to a point. The outer layers rebound in a supernova explosion, bright enough to briefly outshine entire galaxies. But the core continues, falling inward through every possible state of matter, until it becomes something that technically isn't matter anymore. The star's last light marks its transformation into darkness. That supernova flash, by the way, releases more energy in a few seconds than our sun will emit in its entire 10 billion year lifetime. It's one of the most energetic events in the universe, and at the heart of that cosmic firework, quietly, without fanfare, a black hole is born. The universe's loudest announcement paired with its most silent creation. From the brightest death comes the darkest child. Intermediate mass black holes remain one of astronomy's mysteries. We've found plenty of stellar mass black holes, tens of solar masses, and supermassive black holes, millions to billions of solar masses, but very few in between. Where are the black holes weighing hundreds or thousands of suns? Scientists still debate whether they're rare, hard to detect, or form through different mechanisms we haven't fully understood. Some might hide in dense star clusters, revealed only by the subtle motions of nearby stars. A missing middle we're still learning to see. The supermassive black holes at galaxy centers present another mystery. How did they grow so large so quickly? The oldest quasars we observe existed when the universe was less than 1 billion years old. But growing a black hole from stellar mass to billions of solar masses takes time, more time, theoretically, than the universe had at that point. Either black holes grew faster in the early universe, or they somehow started larger than stellar collapse could explain. Seeds planted in the early universe by mechanisms we're still unraveling. Some scientists propose that supermassive black holes formed directly from collapsing gas clouds in the early universe, never bothering with the star stage. These direct collapse black holes might have started with tens of thousands of solar masses, giving them a head start on growth. It's a beautiful idea in the chaos of the young universe. Pockets of gas, dense enough to collapse straight into darkness, avoiding the intermediary step of becoming stars. Skipping straight to the end, written into the universe's beginning, black holes can merge, and when they do, they shake space-time itself. In 2015, the LIGO detectors in Louisiana and Washington state detected gravitational waves for the first time, ripples in the fabric of space produced by two black holes, each about 30 times the sun's mass, spiraling together and merging 1.3 billion light-years away. The final collision, lasting just a fraction of a second, released more power than all the stars in the observable universe combined, the universe ringing like a bell from ancient violence. Those gravitational waves traveled for 1.3 billion years to reach us, carrying information about an event that happened when Earth's most complex life was still single-celled organisms in the ocean. The waves stretched and compressed space-time as they passed, changing the distance between LIGO's mirrors by less than 1,000th the diameter of a proton. We detected the universe's most powerful explosions through measurements smaller than an atom. The largest events revealed through the tiniest changes. When black holes merge, some of their combined mass converts directly into gravitational wave energy. In that LIGO detection, 3 solar masses, 3 times the mass of our entire sun, transformed into pure gravitational radiation in a fraction of a second. Einstein's famous E equals mc in its most dramatic demonstration, mass becoming energy, bending spacetime into waves that carried news of the merger across billions of light-years, matter becoming motion in the fabric of existence itself. Here's something wonderfully strange. Black holes have no hair. This is the actual scientific terminology, the no-hair theorem. It means that black holes are remarkably simple objects, described by just 3 properties: mass, spin, and electric charge. Everything else about the matter that fell in, whether it was stars or planets, hydrogen or iron, old matter or new, is erased. A black hole made from elephants would be identical to one made from light, given the same mass, spin, and charge. All complexity erased, leaving only the simplest description. Black holes spin, and some spin incredibly fast. The fastest spinning black holes we've detected rotate at nearly 99% of the theoretical maximum speeds, so fast that their event horizons drag spacetime around with them, like a whirlpool dragging water. This effect, called frame dragging, means that nothing near a spinning black hole can remain stationary. Even light itself gets caught in the rotation, forced to circle the black hole in the direction of its spin. Space itself becomes a current you cannot resist. The theoretical maximum spin creates something called the ergosphere, region outside the event horizon where space-time rotates so violently that you could extract energy from the black hole's rotation. This is called the Penrose process, after physicist Roger Penrose, who discovered it. You could theoretically drop an object into the ergosphere, have it split apart with one piece falling in and another escaping, and the escaping piece would have more energy than the original object. You'd be stealing rotational energy from the black hole itself. A cosmic battery, theoretically harvestable by advanced civilizations. Stellar mass black holes typically spin because the stars they formed from were spinning. When a massive star collapses, conservation of angular momentum means its rotation accelerates dramatically, like a figure skater pulling in their arms. A star that took weeks to rotate once might become a black hole, spinning hundreds of times per second. All that majestic, slow rotation compressed into a frenetic whirl at the edge of space-time. The star's final dance, accelerated beyond recognition. Supermassive black holes gain their spin through mergers and feeding. Each star or gas cloud that falls in adds its angular momentum, gradually spinning up the black hole. But mergers can also slow spin down if two black holes merge with opposite spins. They partially cancel out. The final spin of a merged black hole depends on the intricate dance of masses and rotations before collision, a cosmic calculation written in the gravitational wave signals we detect. Every merger leaves a signature in how fast the darkness spins. Time slows near a black hole's event horizon. This isn't science fiction, it's measured reality. If you could hover just outside the event horizon of a large black hole while your friend remained far away, you'd experience time passing normally. But to your distant friend, you'd appear to move in extreme slow motion. Wave your hand once, and from their perspective, the wave might take hours. Stay there for what feels like one of your hours, and centuries might pass in the outside universe. Time becomes negotiable near the edge of darkness. This time dilation is why we can never actually see something cross an event horizon. As an object falls toward a black hole, it appears to slow down from our perspective. Its light increasingly redshifted until it seems frozen at the event horizon forever, fading away as its light loses energy. But from the falling object's perspective, nothing special happens at the horizon. It just keeps falling, crossing the point of no return without ceremony. Two truths, both correct about the same moment. If you fell feet first into a stellar mass black hole, you'd be spaghettified. The technical term is tidal disruption. The gravity at your feet would be so much stronger than at your head that you'd be stretched like taffy long before you reached the event horizon of a small black hole. The difference in gravitational pull across your body would tear you apart at the molecular level. Not a pleasant fate, but at least it would be relatively quick, stretched to breaking by the difference in pull across mere feet. But here's something remarkable. With a supermassive black hole, you could cross the event horizon completely intact. The larger the black hole, the gentler the tidal forces at its event horizon. If you fell into a black hole 1 billion times the sun's mass, you wouldn't feel anything special as you crossed the point of no return. You could theoretically float there past the event horizon for hours or even days before tidal forces in the extreme interior finally destroyed you. The bigger the darkness, the gentler the entrance. What happens inside a black hole remains one of physics' deepest mysteries. Our equations break down at the singularity, producing infinities that signal the theories themselves need revision. Some physicists suspect the singularity isn't real, that quantum effects we don't yet understand prevent true infinite density. Others think the singularity is real, but represents a boundary beyond which our concepts of space and time simply don't apply, where math meets its limits, pointing toward truths we haven't learned. Inside the event horizon, space and time swap roles in a sense, just as you can't avoid moving forward in time in normal space. Inside a black hole, you can't avoid moving toward the singularity. The singularity isn't a place in space, it's a moment in your future, as inevitable as tomorrow. You could fire your rocket engines as hard as you liked, and all you'd accomplish is changing when you hit the singularity, not weather. The future becomes a location you cannot avoid. Black holes evaporate, though incredibly slowly. Stephen Hawking discovered in 1974 that black holes emit radiation due to quantum effects near the event horizon. Virtual particle pairs constantly pop into existence throughout space, usually annihilating each other instantly. But near an event horizon, one particle can fall in while the other escapes, and the escaping particle looks like radiation emitted from the black hole. This Hawking radiation means black holes very slowly lose mass. Even darkness eventually fades, though the wait is almost eternal. A stellar mass black hole would take longer than the current age of the universe just to emit the equivalent energy of a candle. A black hole 10 times the sun's mass would take about years to evaporate completely. That's a 1 followed by 67 zeros, an inconceivably vast stretch of time. The universe is currently only about 1,010 years old. Black holes will outlive stars, galaxies, even protons, becoming the last complex structures in an aging universe. Patient darkness, waiting out the cosmos itself. Smaller black holes evaporate faster, and tiny ones would explode. If you could somehow create a black hole the mass of a car, it would evaporate in a fraction of a second, releasing its entire mass as energy in a spectacular explosion. The final moments of any evaporating black hole end in a burst of high-energy particles. But this is purely theoretical. We know no mechanism that creates such small black holes, and any that formed in the Big Bang would have evaporated billions of years ago. Recoil, so violent it can exile the darkness from its home. We've found evidence of these rogue, supermassive black holes wandering through intergalactic space. Observations suggest a few candidate objects with the mass and characteristics of galactic center black holes, but located far from any galaxy. They're cosmic nomads, expelled by their own violent birth, drifting through the void with no stellar court to rule. Lonely giants in the darkness between galaxies, exiled by the force of their own creation. Black holes can have accretion disks that extend for billions of miles. These swirling disks of gas and dust orbit the black hole, gradually spiraling inward. The outer regions can be relatively cool, merely thousands of degrees, while the inner regions rage at millions of degrees. The disk's structure depends on how fast matter falls. In a slow trickle creates a thin, hot disk, while rapid feeding produces a thick, cooler, puffed-up torus. Rings of fire extending farther than planetary systems. Some accretion disks are tilted relative to the black hole's spin axis. This creates a warped disks. The inner regions align with the black hole's spin through frame dragging, while the outer regions remain in their original plane. The result is a twisted, precessing disk that changes its orientation over time. Imagine a vinyl record wobbling on a turntable, but the wobble is caused by spacetime itself being dragged around. Geometry twisted by rotation's grip on space. The innermost stable circular orbit, ISCO, marks a critical boundary. This is the closest distance at which matter can orbit a black hole without inevitably spiraling in. For a non-spinning black hole, the ISCO sits at 3 times the event horizon radius. For a maximally spinning black hole, it's much closer, only 1.5 times the radius. Matter inside the ISCO doesn't gradually spiral. It plunges straight down, crossing the event horizon in a fraction of a second. The last possible orbit before the final fall. X-ray observations can measure a black hole's spin by studying this innermost orbit. Matter at the ISCO emits X-rays with specific energy patterns that depend on how close the ISCO is to the event horizon. By analyzing the X-ray spectrum, astronomers can determine if a black hole spins rapidly or slowly. It's like measuring the rotational speed of something invisible by watching how its accretion disk's innermost edge glows, inferring the invisible through the light at its border. Quasars are supermassive black holes feeding voraciously in the early universe. The term quasar comes from quasi-stellar radio source. When first discovered in the 1960s, they looked like stars but emitted unusual radio waves. Only later did astronomers realize these were actually incredibly distant, incredibly luminous galactic centers. The most distant quasars we've observed are over 13 billion light-years away, showing us black holes as they were when the universe was less than 1 billion years old. Windows to when the cosmos was young and wild. The brightest quasar known, JO 529-4351, outshines 500 trillion suns. Its central black hole weighs about 17 billion solar masses and consumes roughly 1 solar mass of material every day. Every single day, matter equivalent to our entire sun falls into this monster, releasing more energy in 24 hours than our sun will emit in billions of years. It's been doing this for eons, a cosmic furnace that makes our star look like a fading ember. Daily meals measured in entire stars. If you could somehow orbit JO 529-24351 at a safe distance, its accretion disk would appear brighter than thousands of full moons combined. The night sky would be dominated by this blazing ring, casting enough light to read by from millions of miles away. Of course, the radiation would be lethal, but the view would be unforgettably, assuming you somehow survived to remember it. Brightness that would turn night into deadly day. Active galactic nuclei, AGNR, galaxies with actively feeding supermassive black holes. Only a fraction of galaxies have AGN at any given time. Most supermassive black holes, including our own Sagittarius A*, are currently dormant or feeding very slowly. But when a galaxy undergoes a merger or experiences some other disruption that funnels gas toward the center, the black hole awakens, creating an AG, and that can outshine all the galaxy's stars combined. Most galactic centers sleep. Some wake to feed. Blazars are quasars whose jets point directly at Earth. When we look straight down the barrel of a relativistic jet, the radiation becomes incredibly intense due to a phenomenon called Doppler beaming. The jet's motion toward us compresses the light's wavelength and amplifies its intensity. Blazars can vary in brightness dramatically over days or even hours as turbulent structures in the jet move past our line of sight. Looking down the barrel of a cosmic gun, the jet from Blazer 3C 279 extends for over 100,000 light-years, longer than the Milky Way is wide. This coherent stream of particles and magnetic fields, traveling at 99.5% the speed of light, maintains its structure across distances that would take light 100 millennia to traverse. The energy required to launch and sustain such a jet is staggering, drawn from the rotational energy of a black hole billions of times the sun's mass. A spear of energy piercing through a galaxy and beyond. Radio galaxies are similar to quasars, but emit more strongly in radio wavelengths. Their massive jets terminate in enormous lobes of radio-emitting plasma, sometimes spanning millions of light-years. Centaurus A, a nearby radio galaxy about 12 million light-years away, has jets that extend for about 1 million light-years, total roughly 10 times the width of the Milky Way. You could fit dozens of galaxies end to end in the space its jets traverse. Jets outlining volumes larger than galactic clusters. These jets can affect galaxy evolution. The energy they dump into intergalactic space can heat the gas in a galaxy cluster, preventing it from cooling and forming new stars. This AGN feedback is thought to be one of the main reasons why the most massive galaxies stopped forming stars billions of years ago. Black holes don't just consume matter, they regulate star formation across their entire host galaxy, sculpting cosmic evolution. The eater becomes the gardener, pruning galactic growth. Tidal disruption events occur when a star wanders too close to a supermassive black hole. The black hole's tidal force is stronger on the near side than the far sides stretch the star beyond its breaking point. The star tears apart, with about half its material captured into orbit around the black hole and the other half flung away into space. These events produce bright flares of light as the captured stellar debris heats up and begins spiraling inward. A star shredded, transformed from fusion to friction. We observe a few tidal disruption events per year across the observable universe. Each creates a distinctive light signature, sudden brightening in a previously quiet galaxy, followed by a gradual fade over months or years. The spectrum of the light reveals the star's composition, giving us a census of what kinds of stars ventured too close to galactic centers. Most victims appear to be sun-like stars, unlucky enough to pass within the fatal radius. Stars gambling with orbital paths, occasionally losing catastrophically. The tidal disruption radius depends on both the black hole's mass and the star's density. For a supermassive black hole of 1 billion solar masses, a sun-like star would be disrupted at about 3 times the Earth-Sun distance, close enough that the event would occur inside the black hole's event horizon. In that case, we'd never see the disruption because it happens where no light can escape. Only smaller, supermassive black holes, those below about 100 million solar masses, can tidally disrupt stars outside their event horizons. Too massive, and even stellar death happens in darkness. Spaghettification has a technical name. The tidal disruption radius is sometimes called the Roche limit for black holes. It's the distance at which tidal forces overcome a star's self-gravity. For a solar mass star approaching a 10 million solar mass black hole, that's about 100 million kilometers roughly, 2/3 the Earth-Sun distance. Cross that invisible line, and the star begins its final, fatal transformation into a stream of plasma. An invisible boundary marking the beginning of the end. Some stars might survive close encounters. If a star passes just outside the disruption radius, it could be stretched but not destroyed, like taffy pulled but not broken. Such stars would be distorted, losing some outer layers to the black hole, but maintaining their cores. They'd escape the encounter, damaged but alive, carrying scars of their brush with extreme gravity. Survivors bearing the wounds of gravitational violence. Binary star systems complicate tidal disruptions. If a binary pair approaches a supermassive black hole, the black hole's gravity can break them apart. One star might be captured while the other is flung away at high speed. A hypervelocity star ejected from the galactic center at thousands of kilometers per second. These stellar exiles race through the galaxy and beyond, some achieving escape velocity from the Milky Way entirely. Partnerships broken, launching one partner toward intergalactic exile. We've found several hypervelocity stars in our galaxy. US 708, discovered in 2005. travels at about 1,200 kilometers per second, fast enough to escape the Milky Way's gravitational pull. It's thought to be the surviving companion of a white dwarf that exploded in a supernova, with the explosion's asymmetry giving US 708 its tremendous kick. But some hypervelocity stars may owe their speeds to close encounters with Sagittarius A*, our galaxy's central black hole. Stars fleeing the galactic center, never to return. Intermediate mass black holes, the missing link between stellar and supermassive might, hide in dense star clusters. Omega Centauri, a massive globular cluster containing about 10 million stars, shows evidence of a central black hole weighing about 40,000 solar masses. The stars near the cluster's center move faster than they should, unless something invisible and massive pulls on them. If confirmed, this would be one of our best examples of an intermediate mass black hole, a medium-sized darkness in an ancient stellar city. Ultra-compact dwarf galaxies might also host intermediate mass black holes. These tiny galaxies contain millions of stars packed into regions just a few hundred light-years across. Observations suggest several harbor central black holes weighing thousands to tens of thousands of solar masses. These systems might be the stripped cores of larger galaxies, their outer regions torn away by gravitational interactions, leaving only the dense center with its black hole intact. Galactic remnants, reduced to their gravitational hearts. The relationship between black hole mass and galaxy properties fascinates astronomers. Supermassive black holes typically weigh about 0.1% of their galaxy's central bulge mass. This tight correlation suggests that black holes and galaxies grow together, each influencing the other's evolution. But we still don't know if the black hole regulates the galaxy's growth, or if both respond to deeper processes we haven't fully understood. A partnership written in ratios, hinting at deeper connections. Some galaxies deviate from this relationship. NGC 1277, a compact galaxy about 220 million light-years away, has a black hole weighing 17 billion solar masses, about 14% of the galaxy's total stellar mass, far above the typical 0.1%. This suggests unusual formation histories or growth mechanisms. Perhaps NGC 1277 experienced rapid black hole growth early in its life, or perhaps it never formed many stars in its outskirts. Outliers teaching us the rule isn't universal. Dwarf galaxies present another puzzle. Some contain supermassive black holes weighing millions of solar masses, enormous compared to the small galaxies hosting them. How did such small galaxies grow such large black holes? Perhaps they're remnants of larger galaxies stripped down to their cores. Or perhaps small galaxies in the early universe could grow disproportionately large black holes under different conditions than prevail today. Small galaxies with oversized hearts of darkness. Gravitational lensing reveals hidden black holes. When a massive object passes between us and a distant star, its gravity bends the star's light, causing the star to brighten temporarily, a phenomenon called gravitational microlensing. If the lensing object is a black hole, the brightening has a characteristic duration and shape. Surveys monitor millions of stars, searching for these telltale signatures of dark, massive objects passing by. The invisible revealed through borrowed and bent light. Macho searches massive, compact halo objects, looked for dark matter using microlensing. Scientists thought dark matter might consist of dim objects like black holes, brown dwarfs, or rogue planets. Years of surveys found some microlensing events, proving such objects exist, but not nearly enough to account for dark matter. Most dark matter must be something else, probably exotic particles we haven't detected yet, not black holes. A beautiful idea, meeting disappointing data, redirecting the search. Primordial black holes, if they exist, could have a huge range of masses. Some theories suggest they could be as small as a single atom, but contain the mass of a mountain. Others could weigh thousands of suns. These ancient relics from the universe's first moments might be scattered throughout space, invisible passengers accompanying us through cosmic time, formed in the chaos before the first stars ignited. Darkness older than light, potentially surrounding us unseen. The event horizon isn't a physical surface you could touch, it's more like a mathematical boundary in space-time. There's no wall there, no membrane, nothing solid. An astronaut crossing it wouldn't feel anything special at the moment of crossing. It's simply the point beyond which all future paths lead inevitably inward, a one-way gate that exists purely as geometric consequence of extreme mass concentration. A threshold that exists without existing, defined by destiny, not substance. Black holes have temperature, though most are incredibly cold. A black hole with the sun's mass would have a Hawking temperature of about 60 nanokelvins, 60 billionths of a degree above absolute zero. That's colder than the coldest natural place in the universe, colder than anything humans have ever directly observed. Only in laboratory conditions have we reached such frigid temperatures, and even then, only for tiny samples. The darkness is frozen almost to the ultimate limit, but the smallest hypothetical black holes would be scorching hot. A black hole the mass of a car would have a temperature of billions of degrees, radiating intensely in its final moments before evaporating completely. Temperature inversely scales. With mass, the smaller the black hole, the hotter it glows. It's a beautiful irony. The tiniest darkness would shine the brightest. Size and heat moving in opposite directions, defying intuition. Black holes don't violate thermodynamics, despite early concerns. When Stephen Hawking first proposed that black holes have temperature and entropy, it resolved a paradox. Previously, it seemed like dropping a hot object into a black hole would decrease the universe's total entropy, violating the second law of thermodynamics. But Hawking showed that black holes have enormous entropy proportional to their event horizon's surface area, so the total entropy still increases. Even the darkest objects obey nature's fundamental accounting. The holographic principle emerged from black hole thermodynamics. Physicists realized that a black hole's entropy depends on its surface area, not its volume. As if all the information about what fell in is somehow encoded on the event horizon's two-dimensional surface. This led to the stunning idea that perhaps all of three-dimensional space is similarly a projection of information encoded on a distant two-dimensional boundary. Reality as a hologram, suggested by the mathematics of darkness. Black holes might preserve information through Hawking radiation, though we don't know how. When things fall into a black hole, they carry information, their quantum states, their properties, their histories. But Hawking radiation initially appeared to be random thermal noise, carrying no information. This created the black hole information paradox. Does information get destroyed, violating quantum mechanics? Most physicists now believe information survives, somehow, encoded in subtle correlations in the radiation. A paradox pointing toward physics we haven't yet discovered. The firewall paradox deepens these mysteries. Recent calculations suggest that if information escapes in Hawking radiation, the event horizon might not be the smooth, uneventful place we thought. Instead, quantum effects might create a firewall, a region of extreme energy that would incinerate anything crossing the horizon. But this contradicts relativity's prediction that nothing special happens there. Something in our understanding must give. Two beautiful theories disagreeing at the boundary of darkness. Black holes might be connected to white holes, purely theoretical objects that are the time reverse of black holes. While nothing can escape a black hole, nothing could enter a white hole. Matter would pour out of it continuously. If they exist, white holes might be connected to black holes through wormholes, forming bridges through space-time. But we've never observed anything resembling a white hole, and they may be mathematical curiosities rather than physical realities. Darkness with a hypothetical opposite. Light that repels everything. Wormholes, shortcuts through space-time might connect distant regions of the universe, or even different universes. The mathematics of general relativity allows them, and they're intimately related to black holes. A rotating black hole's interior might theoretically connect to another region of space-time. But such wormholes would be unstable, collapsing almost instantly, and crossing one might require exotic matter with negative energies, something we've never found in nature. Cosmic tunnels permitted by equations, forbidden by physics. The Kerr metric describes rotating black holes mathematically, discovered by Roy Kerr in 1963. These solutions to Einstein's equations show that spinning black holes have two event horizons and a ring-shaped singularity instead of a point. The inner horizon hides the singularity, while the outer horizon marks the point of no return. Between them lies the ergosphere, where space-time rotates so violently that nothing can stand still. Layers of boundaries around spinning darkness, each with different rules. The ring singularity of a rotating black hole is theoretically traversable if you could somehow survive the extreme conditions and pass through the ring rather than hitting it. Kerr's mathematics suggests you might emerge elsewhere, elsewhen. The equations permit time travel to the past, travel to other universes, all sorts of exotic possibilities. But most physicists suspect quantum effects or other phenomena prevent these scenarios, preserving causality. Mathematics permitting time travel, physics likely forbidding it. Naked singularities without event horizons are forbidden by the cosmic censorship hypothesis. Roger Penrose proposed that nature somehow prevents singularities from being naked, always clothing them in event horizons. If naked singularities existed, they'd create regions where our physics breaks down but remains observable, leading to unpredictable, possibly paradoxical situations. So far, cosmic censorship seems to hold, though we can't prove it mathematically. A hypothesis that nature is modest, always covering its infinities. Some exotic scenarios might create naked singularities. If you spin a black hole up fast enough by dropping in angular momentum, or charge it up sufficiently with electric charge, the event horizon might theoretically disappear. But calculations suggest that realistic processes can't quite achieve the extreme conditions needed. Nature seems to protect its censorship law through the details of physics. The rules bending but not breaking, preserving the cosmic veil. Black holes can be electrically charged, though most probably aren't. The Reisner-Nordstrom metric describes charged, non-rotating black holes, while the Kerr-Newman metric handles charged, rotating ones. A charged black hole would have different properties, but matter falling into black holes is typically electrically neutral on average, so most black holes carry little net charge. A theoretical possibility, practically rare in the real universe. Magnetic fields thread through black hole accretion disks. These fields, generated by the swirling, charged plasma, play crucial roles in extracting energy and launching jets. The Blandford's-Nyack mechanism shows how magnetic field lines anchored in the ergosphere can tap a rotating black hole's energy, converting rotational energy into electromagnetic radiation and relativistic particle jets. It's one of the most efficient energy extraction processes in the universe. Magnetism as the intermediary between rotation and radiation. Some black holes might have incredibly strong magnetic fields. Magnetar's neutron stars with extreme magnetic fields occasionally collapse into black holes. If angular momentum and magnetic field are conserved during collapse, the resulting black hole could have a magnetic field trillions of times stronger than Earth's. Such fields would affect the accretion disk's structure and jet formation in dramatic ways we're still working to understand. Remnant magnetism from a star's death concentrated into darkness. Black holes can wobble, a phenomenon called precession. If a black hole's spin axis isn't aligned with its accretion disk's rotation axis, the disk's inner regions will precess like a wobbling top. This causes periodic variations in the X-ray and radio emission we observe. V404 Cygni shows this behavior dramatically, with its inner accretion disk precessing every few hours, creating rapidly varying brightness patterns. Cosmic wobbles revealing misalignment between spin and feeding frame dragging near black holes has been measured indirectly. The gravity probe B satellite measured framed dragging around Earth. Our planet's rotation very slightly drags spacetime around it. Near black holes, this effect is millions of times stronger. We see its effects in how accretion disk matter orbits and in the precession of orbital planes. Spacetime doesn't just curve. It flows like a fluid around rotating masses. Space itself caught in the current of rotation. Quasi-periodic oscillations, QPOs, in X-ray binaries reveal inner disk dynamics. These are rhythmic brightness variations in the X-rays, with frequencies that can range from milliseconds to minutes. Different QPOs correspond to different orbital frequencies in the accretion disks, the innermost stable orbit, orbital precession, and other characteristic motions. They're like hearing the beat of matter's final dance before the plunge. Rhythms emerging from chaos. Echoes of orbital mechanics at the edge. High-frequency QPOs can reach 450 Hz. In some systems, that's 450 oscillations per second. Matter is orbiting so fast that it completes hundreds of loops around the black hole every second, just outside the event horizon. At these speeds, the material experiences extreme time dilation, relativistic beaming, and frame dragging effects. It's physics operating at the absolute limits of what matter can survive. The fastest orbital dance in the cosmos, at the boundary of survival. Some black hole systems show low-frequency QPOs that change over time. These might reflect the geometric wobble of the inner accretion disk or instabilities in the flow of matter. When feeding rates change, the QPO frequencies shift, like an engine's note changing with throttle. Astronomers use these variations to map the inner disk's structure and understand how black holes feed under different conditions. Variable rhythms revealing changing meals. Reflection spectroscopy uses iron emission lines to probe the inner accretion disk. When X-rays from the hot disk corona shine onto the cooler disk below, iron atoms absorb and re-emit the radiation at characteristic energies. But near the black hole, relativistic effects distort these emission lines. Some light is blue-shifted, some red-shifted, creating a broad, asymmetric line profile that maps the disk's geometry and the black hole's spin. Iron's signature distorted by extreme gravity, revealing the invisible. The shape of the iron line reveals whether the disk extends to the innermost stable orbit. If it does, the line shows a characteristic broad profile. If the disk is truncated farther out, perhaps because the inner region is filled with hot, optically thin plasmid, the line is narrower. These subtle spectroscopic signatures tell us how matter behaves in the final moments before crossing the event horizon. Spectral shapes as maps of the final approach. NuSTR, a space-based X-ray telescope, specializes in high-energy observations that penetrate deep into black hole systems. Launched in 2012, it has observed dozens of black holes, measuring their spins, mapping their coronae, and studying how jets form. Its observations revealed that some stellar mass black holes spin at more than 99% of the theoretical maximum, nearly as fast as physics allows. A telescope seeing through obscuration to the heart of darkness, the event horizon. Telescope collaboration produced the first black hole images. Using very long baseline interferometry, they linked radio telescopes across Earth in Hawaii, Arizona, Chile, Mexico, Spain, and Antarctica, creating a virtual telescope the size of our planet. The resolution achieved was about 20 microseconds, sharp enough to read a newspaper in New York from a cafe in Paris, if focused on Earth rather than deep space. Planetary cooperation to photograph the unphotographable, the M87 image, released April 10, 2019, showed a bright ring of emission around a dark central shadow. That shadow is about 2.5 times the size of the event horizon. It's not the event horizon itself, but the photon sphere, where light orbits the black hole before escaping or falling in. The asymmetric brightness in the ring comes from the disk's rotation and relativistic beaming as material moves toward us on one side and away on the other. A shadow cast by gravity itself, outlined in orbiting light. Creating that single image required petabytes of data. Each telescope recorded so much information that it couldn't be transmitted over the internet instead. Hard drives had to be physically flown to central processing facilities. The data from the South Pole telescope had to wait months until the Antarctic winter ended and planes could land. Then supercomputers spent 2 years processing the observations, calibrating instruments, and producing the final image. A photograph requiring the patience of seasons and the work of hundreds. The Sagittarius A** image, released May 12, 2022, showed our own galaxy's central black hole. SGR-A** is much smaller than M87's black hole, so material orbits much faster, completing circuits in minutes rather than weeks. This made imaging harder because the accretion disk's structure changed significantly during observations. The team had to develop new techniques to account for this variability, essentially creating thousands of snapshots and combining them into a stable image. Our own galactic center, finally visible through years of effort. Both images confirmed general relativity's predictions with stunning precision. The size and shape of the shadows matched theoretical calculations based on the black hole's masses measured through stellar orbits. Einstein's equations, developed over a century ago with no knowledge of black holes, predicted exactly what we would see when we finally photographed one. Theory meeting observation at the edge of spatial IME. Future Event Horizon Telescope upgrades will add more telescopes and observe at higher frequencies. This will sharpen the images, potentially revealing the jet's launch points and the magnetic field structures threading through the accretion disks. We might even see time-lapse movies of matter swirling into black holes, watching dynamics unfold over days or weeks. From single photographs to motion pictures of feeding darkness, space-based gravitational wave detectors will hear supermassive black hole mergers. LISA, the Laser Interferometer space antenna planned for launch in the 2030s, will consist of 3 spacecraft flying in formation 2.5 million kilometers apart. This enormous triangle will detect gravitational waves from black holes millions or billions of times the sun's mass. Mergers to slow and low frequency for ground-based detectors to hear. Listening posts in space. Tuned to the deepest cosmic bass notes, these supermassive mergers will be visible across the entire universe. While LIGO can only detect stellar mass mergers within a few billion light-years, LISA will hear supermassive black hole mergers from when the universe was young. We'll detect these events years before they happen. Gravitational waves will arrive before electromagnetic signals, giving us advance warning to point traditional telescopes at the source. Hearing the future, in a sense. Through gravity's early arrival, pulsar timing arrays offer another way to detect gravitational waves. Astronomers precisely monitor millisecond pulsars, rotating neutron stars that pulse like cosmic lighthouses with extraordinary regularity. Gravitational waves passing between Earth and these pulsars subtly change the pulse arrival times. By monitoring dozens of pulsars across the sky, we can detect very low-frequency gravitational waves from supermassive black hole binaries throughout the universe. The cosmos as a detector, pulsars as its sensors. In 2023, multiple pulsar timing arrays announced evidence for a gravitational wave background, a constant hum of gravitational waves filling space, likely from countless supermassive black hole mergers throughout cosmic history. It's like standing in a crowded room and hearing the combined murmur of many conversations. Except these conversations are black holes, millions of light years away, merging across billions of years. The universe humming with ancient collisions, a chorus of gravity. Black holes might seed galaxy formation in the early universe. Some theories suggest that primordial black holes, or the first generation of supermassive black holes, acted as gravitational anchors, helping gas collect and galaxies form. The black hole would sit at the center, its gravity gradually pulling in surrounding matter, building the galaxy around itself like a pearl forming around a grain of sand. Darkness as the seed around which light eventually gathers. The first star's population. Stars were probably much more massive than modern stars. These primordial giants formed from pristine hydrogen and helium with no heavier elements could have been hundreds of times the sun's mass. When they died, they might have created the first black holes, seeding the universe with darkness before the second generation of stars even ignited. The universe's first darkness, born from its first light's death, some population 3 stars, might have collapsed directly into black holes without exploding. If massive enough, perhaps 260 solar masses or more, these stars would be completely disrupted by parent stability, leaving nothing behind. But in a narrow mass range around 140 to 260 solar masses, they'd produce spectacular supernova. Below about 40 solar masses, they'd explode as normal supernova. And above 260 solar masses, they'd collapse directly, silently becoming black holes with no supernova at all. Different masses leading to different fates. Written in Stellar Evolution. Quasistars are hypothetical objects from the early universe stars with black holes at their cores. In the dense, hot conditions of the very early universe, a black hole might form inside a massive envelope of gas. The black hole would feed on the surrounding gas, releasing energy that supports the envelope against collapse. These objects could grow to thousands of times the sun's mass, potentially explaining how supermassive black holes grew so large so quickly. Stars with hearts of darkness, supporting themselves through feeding. Black holes in the early universe grew faster than today. The gas was denser, galaxies merged more frequently, and supermassive black holes had abundant fuel. Growth rates that would take trillions of years today happened in mere hundreds of millions of years then. The early universe was a feast for black holes. The modern universe offers only occasional snacks. Youth's abundance versus age's scarcity. Written in feeding rates. Some galaxies show evidence of past quasar activity, but are now quiet. Our Milky Way was probably more active billions of years ago when gas was more abundant. Sagittarius A** might have been a bright quasar then, its jets and radiation reshaping the galaxy. Now it slumbers, only occasionally flickering when a gas cloud or unlucky star wanders too close. Every supermassive black hole has a history, most now retired from glory. The Fermi bubbles above and below our galaxy's center might be remnants of past activity. These enormous structures, extending 25,000 light-years from the galactic plane, glow in gamma rays and may represent the ghosts of ancient jets from Sagittarius A**. They suggest that just a few million years ago, recent in cosmic terms, our galaxy's central black hole had a major feeding episode. Evidence of recent activity painted across thousands of light years. Supermassive black holes can regulate star formation across entire galaxies. When they feed actively, their jets and radiation heat the surrounding gas, preventing it from cooling and condensing into new stars. This feedback mechanism might explain why the most massive galaxies stopped forming stars billions of years ago. Their central black holes grew large enough to effectively shut down star formation. The gardener pruning its own garden, limiting growth through influence. But black holes can also trigger star formation. Jets plowing through interstellar gas can compress it, creating dense regions where stars form. Outflows from accretion disks can do the same. So black holes both suppress and stimulate starbirth. Their influence on galaxy evolution, complex and multifaceted, creation and destruction emerging from the same source, simultaneously building and destroying, the duality of cosmic influence. Black hole mass correlates with the velocity dispersion of stars in galactic bulges. Faster-moving stars indicate more massive bulges, which host more massive black holes. This M-sigma relation is a remarkably tight measure, the random velocities of stars in a galaxy's center, and you can predict the central black hole's mass with good accuracy. It reveals a deep connection between black holes and their host galaxies. Motion revealing mass, relationships written in stellar velocities. But we don't fully understand why this correlation exists. Do black holes grow until they're massive enough to shut down their own growth through feedback? Do they grow together with their galaxies through some shared process? Or do both respond to deeper factors in galaxy formation? The correlation is clear. The causation remains mysterious. Observations ahead of understanding, as often happens in science. Ultra-luminous X-ray sources, ULXs, in nearby galaxies might be intermediate mass black holes. These objects shine too brightly to be stellar mass black holes feeding normally. Yet they're not in galactic centers where supermassive black holes reside. Some might be stellar mass black holes feeding at super-Eddington rates exceeding the theoretical limit where radiation pressure should blow away in falling matter. Others might genuinely be intermediate mass black holes, the missing links we've sought. Extraordinary brightness pointing toward extraordinary masses or extraordinary physics. The Eddington limit describes the maximum luminosity for a given mass when radiation pressure from emitted light equals gravitational attraction pulling matter inward. The system reaches equilibrium. For our Sun, the Eddington luminosity is about 30,000 times its actual output. Tower star is a gentle, steady burner. For actively feeding black holes, the Eddington limit is often the actual feeding rate, the maximum sustainable brightness. A balance between inward pull and outward push, setting brightness limits. Some sources exceed their Eddington limits. Super-Eddington accretion occurs when matter falls in so fast that radiation can't escape efficiently. The accretion flow becomes thick and opaque, trapping radiation inside. The black hole can feed faster than naively expected. Though the efficiency drops, less energy escapes per unit mass consumed. It's like eating too fast to taste your food. Sometimes the limit is a suggestion, not a law, under extreme conditions. Tidal disruption events can create super-Eddington flares. When a star is shredded, a huge amount of matter suddenly becomes available. For months or years, the black hole feeds far above its Eddington limit, creating an extraordinarily bright flare. These events let us study super-Eddington physics and reveal black holes in otherwise quiet galaxies. A sudden feast breaking all the usual rules, briefly outshining galaxies. At 2018, Cow named the Cow was an unusual transient event that might have been a tidal disruption. Discovered in 2018, it brightened and faded far faster than typical supernova, and it emitted unusual amounts of X-rays and radio waves. Some astronomers think it was a star torn apart by an intermediate mass black hole, while others propose it was a new type of supernova. The Cow remains mysterious, a reminder that the universe still surprises us. Nicknamed for its astronomical designation, puzzling us still. Black holes can have heartbeats, regular pulsations in their brightness. GRS 1915 plus 105 shows a repeating pattern every 50 seconds or so, like a cosmic pulse. These oscillations might reflect instabilities in the inner accretion disk, cycles of accumulation and ejection, matter building up until radiation blows it away, then building again, rhythm emerging from instability, a mechanical heartbeat in darkness. Some black holes show state changes, transitions between different accretion modes. They might spend years in a hard state with weak X-ray emission and strong radio jets, then suddenly switch to a soft state with bright X-ray emission and weak jets. These transitions happen over days or weeks, dramatic reorganizations of the accretion flow's geometry and physics, shifting between modes like a machine changing gears for reasons still debated. The innermost regions of black hole accretion disks reach temperatures of billions of degrees. At these extremes, photons carry enough energy to spontaneously create particle and antiparticle pairs. The disk becomes a cauldron of matter and antimatter, creation and annihilation, particles winking in and out of existence, all within the grip of extreme gravity just outside the event horizon. Matter and antimatter dancing at the edge, born from pure energy. Accretion disk winds carry away significant amounts of matter. Not everything spiraling toward a black hole makes it in. Radiation pressure and magnetic forces drive powerful winds that blow matter away. Some estimates suggest 90% or more of the matter that falls toward a black hole gets ejected before crossing the event horizon. The winds carry energy and momentum outward, affecting the surrounding galaxy. Most of what falls also rises, in a sense, blown back by the feeding process. Black holes might be connected to dark energy through quantum effects. Some speculative theories propose that the interiors of black holes could contribute to dark energy, the mysterious force accelerating the universe's expansion. As black holes grow more common and massive over cosmic time, they might influence the universe's expansion rate. It's a fringe idea, not widely accepted, but a fascinating attempt to connect black holes to cosmology's biggest mystery. Darkness within, perhaps connected to darkness without, speculatively. The ultimate fate of black holes is evaporation through Hawking radiation. In the unimaginably distant future, 10,100 years from now, even the largest supermassive black holes will have radiated away completely. The final moments of each will be explosive, a brief flash of high-energy particles, marking the end of the last complex structures in an aging, dying universe. And then only darkness and sparse radiation will remain. The last light in the universe might come from black holes dying, but that's trillions upon trillions of years away. For now, black holes are vibrant participants in cosmic evolution. They shape galaxies, launch jets, create the brightest objects we observe, and bend space-time in ways that test our understanding of physics. They are laboratories of extreme conditions, windows into quantum gravity, and monuments to the power of mathematics to predict nature's strangest manifestations. Active players in the current cosmic drama, despite their dark reputation. We've barely begun exploring black holes. Each new observation reveals surprises: black holes more massive than expected, mergers happening faster than predicted, relationships with galaxies more complex than simple models suggested. We've photographed them, heard them collide, measured their spins, but countless mysteries remain. The journey of discovery continues, each answer raising new questions. Perhaps one day we'll understand what happens at the singularity. Whether information truly escapes, how the first supermassive black holes formed so quickly, what dark matter truly is, whether naked singularities can exist, and how quantum mechanics and gravity unify. Each question points toward deeper understanding, new theories, expanded knowledge of the cosmos and our place within it. Questions as valuable as answers, pointing toward future understanding. For now, we can marvel at what we've learned, that massive stars end their lives collapsing into regions of space-time so warped that nothing escapes, that these invisible monsters reveal themselves through their gravitational embrace of companion stars, through the light of matter spiraling to its doom, through gravitational waves ringing across the universe, that supermassive black holes sit at the hearts of galaxies, including our own, simultaneously destroying and creating, consuming and illuminating. The paradox of darkness creating light, destruction enabling creation, and we can appreciate the human achievement behind these discoveries. Generations of scientists building upon each other's work, from Einstein's equations to Schwarzschild's solutions, from Chandrasekhar's limit to Hawking's radiation, from LIGO's detection to the Event Horizon Telescope's images, mathematics, engineering, international cooperation, and sheer human curiosity combining to reveal nature's most extreme phenomena. Minds across time working together, unveiling the invisible. We've traveled far tonight, you and I, from the nearest black hole, just 1,600 light-years away, to the most distant quasars, over 13 billion light-years distant. From stellar mass black holes you could drive across in minutes to supermassive monsters whose event horizons span light days. From the mathematics of singularities to the observed reality of shadows cast by gravity itself. Along the way, we've encountered mysteries, the missing intermediate mass, black holes, the information paradox, the firewall problem, the question of how supermassive black holes grew so quickly. We've found unexpected connections between black holes and galaxy evolution, between the darkest objects and the brightest phenomena, between the smallest quantum effects and the largest cosmic structures. But more than facts and figures, I hope you've felt the wonder, the strange beauty of a universe that creates such objects, the elegant mathematics that predicted them before observations confirmed them, the human persistence that finally photographed them, the cosmic creativity that transforms massive stars into regions where time slows and space curves back on itself. Black holes remind us that the universe is far stranger and more magnificent than everyday experience suggests, that reality operates on scales both vast and tiny that challenge imagination, that mathematics can be a language describing nature's deepest truths, that curiosity and careful observation can reveal what seems impossible. As you drift toward sleep, perhaps you'll dream of accretion disks glowing brighter than galaxies, of gravitational waves rippling through space-time, of event horizons marking boundaries we can calculate but never cross. Perhaps you'll imagine the slow dance of binary black holes spiraling together over millions of years, or the instant of merger that shakes the universe with gravitational song. Or perhaps you'll simply rest in the knowledge that the cosmos is full of wonders we're still discovering, that each generation unveils new mysteries and solves old ones, that the universe we inhabit is both comprehensible and strange, governed by laws we can understand but manifesting in ways that astonish. Thank you for joining me on this journey through the darkness that creates light, the simplicity that produces complexity, the mathematics that predicts reality. May your dreams be filled with cosmic wonder, and may you wake refreshed, carrying a little of that wonder into tomorrow. The universe continues its slow dance, black holes feeding and merging, stars being born and dying, galaxies evolving across billions of years. And you are part of it, all made of atoms forged in stars, living on a planet orbiting a star in a galaxy with a black hole at its heart, observing and understanding the cosmos that created you. Rest well, traveler. The mysteries will still be here tomorrow, waiting to inspire new questions, new observations, new understanding. Good night.